Okay, so remember what we were talking about? Taylor series, right? Right? Taylor series, right? So you have some function, right? The function is infinitely differentiable on some interval a minus epsilon, a plus epsilon, right? So there's some point A, and you have an interval centered around A, and the function is infinitely differentiable there. Okay, then we create, we call, remember, so we call, if this thing is infinitely differentiable, then we call a certain polynomial, right? I'm sorry, a certain power series. We call this power series the Taylor series centered at A, centered at A, associated with F. Okay. So you have this function, and you make this power series out of it, right? This guy is called the Taylor series. And what we said last time was there's no guarantee that the Taylor series actually recovers F. Right? There's no guarantee that this Taylor series actually equals your function. Okay. We gave an example of a function where the Taylor series was 0 everywhere, right? Even though the function wasn't the 0 function. Okay. So that's what our question is can we give some conditions that ensure that it does? Okay. Can we give some conditions that ensure that the Taylor series actually does recover your function? Okay. So let me just introduce some terms that we're going to use to talk about this question. Okay. So here's the definition. We call the sum of these the power series from k equals 0 to n, the nth Taylor polynomial. Nth Taylor polynomial of f around A. Okay, so that is you take your power series and you just truncate it, right? You stop it at capital N. The nth Taylor polynomial of f around A. The nth Taylor polynomial of f around A. Okay, so just let's make this concrete. Remember, so just keep something in your head. E to the x, if we look at the Taylor series around 0, it turned out to be 1 over k factorial x to the k. Right? This is the Taylor series around 0. Okay. The Taylor series around 0 turned out to be this guy. Okay. And if I'm talking about the nth Taylor polynomial, it means that I'm going to go out to the nth power, right? So I'm going to go 1, well, like if I say so 1, this would be 1 plus k x squared over 2 factorial plus x to the n over n factorial. Okay, and that would be called the, sorry. If we stop it at the nth power, then that's called the nth Taylor polynomial. Okay. Right. So let's call this. Let's give this. Let's call this thing p sub n. P sub nx. Okay. P sub nx for the nth Taylor polynomial. Let p sub nx denote this nth Taylor polynomial. Okay, so this is the partial sum, right? This is the partial sum of the Taylor series. This is the partial sum of the Taylor series. Okay, right? That's all this is, right? The partial sum of the Taylor series. Right? So our question is, when does the partial sum series, right, recover your function? Right? When does the partial sum series recover your function? That's really our question, right? Is everybody following the story? Okay. So let me rewrite that. That's when does the limit of the function minus the partial sum series go to 0? Right? When does the difference go to 0? Right? When does the difference go to 0? We call this thing the remainder. Okay, R sub n. This thing, this difference we call the remainder, right? The remainder, right? Or you can think of it as the error, right? This is really the error, right? And so our question is, when does the error go to 0, right? Okay. Right. So we've just taken our question and rephrased it slightly. Right. So here's the theorem that gives us the answer. This is called the Lagrange Remainder Formula. Okay. And it gives you basically so it gives a control on the size of the error. Okay, it gives a bound, to use the mathematical word, it gives a bound on the size of the error. Okay. I should say, sorry, that's not quite precise. Can be used to give a bound on the size of the error. Okay, so here it is. So if f has n plus 1 continuous derivatives, in some neighborhood a minus epsilon, a plus epsilon. Then, so let me call this thing I for interval. In some interval I, maybe I just should say some interval I around A. Then for each x in that interval, there is a C between x and A where the error equals where the nth error equals f to the n plus 1, I'm sorry, the n plus 1th derivative of f evaluated at c over n plus 1 factorial x minus a to the n plus 1. Okay, so let me again. That's very abstract. Let me make it concrete with the example. So so here's how you want to think. Okay, so let's remember our example. F of x is e to the x, and the nth Taylor polynomial is 1 plus x plus x to the n over n factorial. Okay. And we're wondering how wrong this is. Okay, so okay, so let's make it really concrete. When we say the fourth Taylor polynomial, we mean 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. Okay. Okay. And suppose somebody wants e to the 1. Okay. You want to figure out what e actually is. Okay. And so you say, well, I know that I have this Taylor approximation, so I know that this is going to be something like 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial. Okay, right? That's your Taylor polynomial. Right? This is p sub 4 at 1. Right? And this is your function at 1. Okay. And so the Lagrange Taylor formula, the Lagrange remainder formula says that the difference between this, right, that the error R4 at 1 actually equals the fifth derivative of f evaluated at c over 5 factorial times 1 minus 0 to the 5. for some c between 1 and 0. Okay. Okay. Does that make the statement clear enough for you? I hope. Right? Right? It says that if you have some function and you're trying to figure out the error, well, the error actually equals the nth plus 1th derivative of your function evaluated at some point between x and a times x minus a to the n plus 1 over n plus 1 factorial. Okay, so here, right, we've got our, here is 0, here is 1, right, and the remainder formula says, well, there's some point between 0 and 1 where the remainder actually equals the 5th derivative valued at that point. For this guy, we actually know the 5th derivative, right? It's just e to the x. So this is going to be e to the c, right? It's going to be e to the c, but the remainder is going to be e to the c. It's going to be e to the c over 5 factorial, right? E to the c over 5 factorial. Okay. Right. Okay. So. Okay, so this gives us a way to control. This gives us some knowledge about how wrong we are, right? How wrong we are, right? You know that so that's the statement of the theorem. Okay, you know exactly how wrong you are, right? There's some point in between 0 and 1 where the error is e to that point times x minus a to the 5th over 5 factorial. Any questions? Yeah, Franco.
Why is it between 1 and 0?
It actually has to do with the mean value theorem. It actually has to do, if you get into the proof of it, it actually has to do with, do you remember the mean value theorem says that between here and here, there's some point where something special happens. Okay. This C actually, we actually gave the proof of it, comes out of the mean value theorem.
Do we always choose C between 1 and 0?
So it's between the point of evaluation and the center of your power series. Okay. So you're taking your power series around A, right? Right. So this is the error between f of x and your power series the difference between this and your power series centered at your Taylor polynomial centered at A. Okay, sorry, I should have said this. This is actually important, so please note this down. Yeah, Mr. L.
So in the example that you gave,
Yeah.
the 65/24, which is, if I add up to the fourth derivative, is in error by 1 over 120 times f prime of whatever point I take. Is that correct?
That's right. That's right. This is how wrong that number is. So what is this number? You worked it out, it seems.
It's, well, it's going to be 65/24.
65/24. Okay. 65/24. Okay. So yeah. So this number is a good approximation for E up to this error. Okay. Okay. So yeah, Ian.
And on the final exam, because we don't have calculators, what would this be like?
So I'll have to explain it next time. So yeah, I'll get to that in the next part of the lecture. Okay. So at this point, though, I just hope that you understand the statement of the theorem. Okay. The theorem says, that if you're trying to approximate your function, then the error looks like this. Okay. That's all I want you to get. Okay. So So next time we'll talk a little bit. We'll talk about how to make this a little bit more usable. Yeah, man.
Will we ever actually find the value of C?
No, you see, that's the thing. Okay, so okay, but we do know that C is smaller than 1, right? So e to the C is smaller than e to the 1. Okay, so this is what I meant by you can use it to get a bound. You can use it to get a bound on the error size, right? The bound is going to be smaller than e over 120, right? Or, and e is smaller than 3, say, so you know that it's smaller than 1/40th. Okay, so let's stop here because I want to do course evaluations.